In this talk, I'm going to present the insights we gained from combining static analysis error traces with dynamic symbolic execution. This is joint work with Pritam Garat, Christian Kadar, and Alistair Donaldson. Static analysis is a program analysis technique that is reasonably fast and can easily be integrated into the development cycle. But to be fast, static analysis engines over-approximate and therefore report false positives, sometimes in such large numbers that developers begin to ignore the reports or refuse such tools. On the other end is dynamic symbolic execution, a precise technique that only reports true positives. However, dynamic symbolic execution is expensive, as it tries to explore all interesting, if not all paths through a program. In this work, we take so-called traces, error reports with path information from static analysis engines, and use those to guide a dynamic symbolic execution engine. The overall aim is to confirm the true positives and provide test cases for easy debugging to the developers. Allow me a short disclaimer here. In this paper, we combine the traces of two specific static analyzers with one symbolic execution engine in a particular way. We do not compare static analysis and symbolic execution. We do not generalize our results to any combination of static analysis and symbolic execution. And we do not benchmark static analyzers against each other. Still, we found our results surprising and think that they could be useful for the community. Let me show you a contrived example. This program has three input variables in 1, 2, and 3. For the sake of simplicity, they are just copied from the first command line argument to the program via argv. Additionally, there are two pointers, P0 and P1. For P0, it actually allocates memory and writes the first input byte to that location. At the end of the program, we copy that memory content back into a variable result, freeze the memory, and return result. So far, so good. However, when the first input byte equals uppercase H and the second is I, we alias the pointer P1 with P0. If additionally the third input byte is an exclamation mark, we freeze the alias pointer P1. That means at the end of the program, we dereference invalid memory and illegally freeze the memory a second time. As you can see on the right side, when we run the program with input foo, nothing happens. When we pass hi to it, exec faults. Why does it crash for the third input? Well, I added a while loop around the if statements where I decrement the first byte to make the program slightly more interesting. Now, when we analyze this program with a static analyzer, here Clang static analyzer, it finds the bug and gives us a detailed trace to reproduce the bug. The trace is here shown in a developer-friendly way in the browser. Simplified, it says, first allocate memory in line 10, then enter the loop. For all three if statements, take the true branch, freeze the memory, iterate the loop one more time due to our loop condition, then exit the loop, and finally hit the bug in line 23. Unfortunately, sometimes such traces cannot be followed as they are infeasible. We give an example for an infeasible trace from infer, another static analyzer, in the paper, but you can see here on the left side that the Clang static analyzer sometimes gets confused as well. Do sandbox at the top has to be false, whereas a few steps further down at the bottom it has to be true. This is a contradiction as that variable is not changed in between. A dynamic symbolic execution engine, such as CLE here, runs the program, explores all paths, and finds that bug as well. But you can see, even for that small example, it explores 554 execution paths. It is able to write tests for all paths, but I configured it here to only write tests for paths that covered new code or reached a unique error. Hence, it only wrote 4 tests. So why 554 paths? A symbolic execution engine works on symbolic placeholder inputs, opposed to concrete values. In this example, I marked 3 bytes of the first command line argument as symbolic via the symarg flag. And those bytes become in 1, 2, and 3 in the program. When the symbolic execution engine reaches a condition with a symbolic value, like the while loop or the if statement, it checks whether the true and false branches are feasible with the help of an SMT solver. If both branches are feasible, it splits the execution path, attaches the condition or its negation to the respective sites, and explores both branches. In our example, it first reaches the while loop. In1 is completely unconstrained, so there exist values for in1 where the loop condition is true or false. CLE at that point splits the execution. the false branch never reaches the loop body and just continues until it terminates, whereas the true path enters the loop. Then it hits the first if statement, and again, CLI checks the feasibility, and as both sets are feasible, splits the execution. The false path goes back to the loop header, and the true branch reaches the next if statement, and so on. The red dot marks the path where the error manifests. Please note that the first if statement basically concretizes the value for in 1. It has to be uppercase H. That means the true branch forms a relatively small subtree, whereas the false branch decrements in 1 and returns to the loop header, causing the execution to branch again on the first if statement. This iteration pattern repeats until the domain for in1 is exhausted. When we zoom out a little bit, the execution tree looks as shown on the right side. As before, the red dots mark all paths where the bug manifests, and the green dots represent the paths where the first byte is uppercase H, but the second and third bytes are not I and exclamation mark. In what order this tree gets explored is determined by an exploration strategy or search heuristic. So this is a very important component, especially for large programs, as it depends on this component what parts of your code actually are covered and when. Our setup is structured as follows. We use 2 open source static analyzers, Clang Static Analyzer and Infer. Both can handle C, C++, and Objective-C and return traces and not just error locations. We pass those traces into a custom format, instrument the source code individually for each report, compile the sources to LLVM bitcode, and run the instrumented program with a modified version of the CLI Symbolic execution engine. An instrumented program looks as follows. For every step in the trace that tells us what condition has to hold or not, we insert a function call such as install line 13 in the while condition or install line 14 for the first if statement. We also mark the final bug location with another function call, here install line 23. Each of those functions contains one or more calls to assume SA. This is an intrinsic function that is handled by the execution engine directly. The first parameter is the step number, the second one the condition. The instrumentation function for the while loop condition, shown left, contains 3 calls. 2 for the first 2 iterations where the condition is true, and the third one, step 8, where it exits the loop. In case you're wondering why those calls are ordered in reverse order, this is an easy way to handle multiple steps in a single location. If one would not reverse the order, step 7 would be executed and step 8 immediately afterwards in the same call, without iterating the loop one more time. This is not what we want, and the reverse order prevents it. We have implemented 3 ways to handle such assume SA calls. The first is ignore. The execution engine does nothing basically in this case. We use this, for instance, for the baseline experiments. The second one, the strictest one, is require. Here all constraints have to hold, otherwise the path gets terminated. And in between is try. This strategy checks if a condition holds. If it holds, it is appended as path constraints, otherwise it is ignored. We hope that this could aid funding true positives with both traces or other shorter paths to a true positive. Remember, CLI executed 554 paths for our example. When we apply CLI now to our instrumented code and use the stricter strategy that enforces that all conditions hold, CLI only has to execute a single path and a fraction of the instructions. But there's another way to take advantage of the instrumentation. CLI is an EGT-style symbolic execution that keeps all unfinished paths in memory and selects paths for further exploration with different search heuristics. Given that our goal is to execute the trace steps, represented by the instrumented locations, we added a new search heuristic that steers the execution towards those locations. Let's assume we have an interprocedural control flow graph as shown on the right, and 3 instrumented steps, the last one being the final error location. Furthermore, the symbolic execution engine explores 3 paths in that CFG currently. Our targeted search heuristic now prioritizes paths that have already reached the highest number of steps, and among those, the ones that are closest to the next step. The heuristic has some more features. For instance, we terminate paths that can't reach the error locations, but we keep paths that just can't reach some intermediate steps. In that case, they just target the next reachable step. If you'd like a more detailed description, please have a look at our paper. For the evaluation, we tried to use real-world bugs. For that, we investigated historical bug reports from static analyzers. We also analyzed core bench, a corpus of 70 regression errors, And finally, we ran Inferred Clang Static Analyzer on 25 applications or application suites that were older than 7 years and contain known bugs. To summarize, we found almost no historical bug reports and couldn't find known bugs in Core Bench with our static analyzer. For the older applications on the right side, we investigated up to 20 bug reports per benchmark. Both analyzers returned roughly 300 reports for memory-related bugs. The reports we inspected were either false positives or trivial true positives. Especially Infer returned many trivial true positives, such as missing return value checks for malloc or local time. And there are two issues with such reports. First, CLI does not model such errors. And second, many programmers nowadays do not consider these as bugs due to Linux's overcommitment for memory allocation, for instance. So we had to fall back to artificially inject bugs. We inject two kinds of bugs: null pointer dereferences and use after free errors. A use after free error can be seen on the right and is similar to the pattern I showed you in the example. It contains two pointers, one gets initialized, the other one becomes an alias. After freeing the original pointer, the alias gets illegally dereferenced, possibly causing a crash. If all those instructions for an error are placed in a single source code line, we call it a one-event bug. If the instructions are spread over several source locations, we call it 2, 3, or 4 event bug, respectively. All bugs were injected along feasible paths and in locations that are hard to reach for CLI. More concretely, where CLI needed 10 to 120 minutes to cover the original source line. As applications, we used 10 reasonably deterministic core utils. We injected several 101-4 event bugs, and as you can see in the figure on the right side, static analyzer struggled to find 2, 3, and 4 event bugs. With one exception, Clang Static Analyzer does quite well for two-step use after free bugs. For one-event bugs, Clang Static Analyzer performs really well and finds more than 88% of the bugs, whereas Infer only finds 53 of the null dereferences and 15% of the use after free errors. For further evaluation, we selected 55 of the found bugs and ran the instrumented programs with our version of CLI. The y-axis shows the total runtime for CLI. CLI either terminated when it found a specific bug or after a deadline of 2 hours. The numbers above the bars show the number of detected errors. The blue bars show the ignore strategy, where we ignore the conditions in instrumented steps. The red bars show the require strategy, the strictest case, where all conditions have to hold or path gets terminated otherwise. The orange bars show the try strategy, where we test each condition and only attach it as a path constraint to path when it holds. In each box, you can see two bars, a brighter and a darker one. The darker ones are the results for our targeted search heuristic, and as expected, it works better than the default search heuristic. It needs less time to reach more bugs. The other results were more surprising. First, the strictest strategy require finds only half of the bugs in comparison to ignore and try, meaning being less strict about the conditions given in the trace is actually beneficial. But when we compare try and ignore, we can see that both perform almost identical. That means the conditions in the trace steps are not very helpful or often implied by the path to the error. At that point, we were wondering how useful the actual intermediate step locations in the trace are. So we modified our search heuristic to ignore intermediate steps completely and only target the final error location. And as you can see, surprisingly, the green bar shows comparable results to the best performing combinations and finds all bugs. And with this, I come to the bottom line of my talk. The static analysis traces in our experiments in general do not add any benefits when combined with targeted symbolic execution. That's it from my side. Please ask any questions that you might have. And if you are interested in symbolic execution, please join us for the third International CLI workshop in symbolic execution in September.